Welcome to the Explainer. Have you ever looked at a really complex function and just wished you could make it simpler? Well, today we're going to unlock one of the most powerful tools in all of calculus, the Taylor series. This thing is a total game changer, so let's just dive right in. Okay, so let's really get into the main idea here. A lot of the time in calculus, right, we're wrestling with these messy, complicated functions. But what if? What if we could just translate them? What if we could take something like sine of x and rewrite it as something super simple, like a basic polynomial that just uses addition and multiplication? And that, right there, is the magic of the series method. The whole idea is to take any function that's well-behaved, one that's smooth and you can take the derivative of over and over again, and represent it as an infinite sum of simple polynomial terms. Seriously, it's like building a really complex curved statue using an endless supply of simple, straight Lego bricks. So how do we actually do this? What's the blueprint for building our Lego statue? Well, it all comes down to one really powerful formula. Let's break this down, because every single piece here has a really important job. You see that derivative part? That's what matches the function's slope and its curve and all its other behaviors, all at one single point. Then you've got the factorial on the bottom, which keeps all the terms scaled just right. And that part that says x minus x naught, that's what lets us choose the exact point where our approximation is going to be the most accurate. This thing is literally the recipe for rebuilding a function from the ground up. Now look, you could build every single series from scratch using that formula, but that is the long way around. Trust me, the real shortcut, the pro move, is to have a toolkit of the most common series already memorized. So let's look at the essentials that are going to save you a ton of time. This table shows you the big four. And a Maclaurin series, by the way, is just a fancy name for a Taylor series that's centered at 0, which is what you'll see most of the time. You've got e to the x, sine, cosine, and the geometric series. Seriously, committing these patterns to memory is the single best shortcut you can have for these kinds of problems. It's the difference between solving something in 2 minutes versus like 20 minutes. Okay, so we have the main formula, and we've got our toolkit of common series. Now let's put this theory to work. Let's see how we can combine these tools to solve some new, more interesting problems. Here is a classic exam-style problem. Find the series for x times e to the x. Now, instead of starting from scratch and taking all those derivatives, we can be a little more clever and just use your toolkit. And the process is actually wonderfully simple. You just write down the series for e to the x that we already memorized from our toolkit. Then, since our new function is just that series multiplied by x, well, we just multiply the whole thing by x. A little bit of algebra to clean it up, and boom, there's our answer. No messy derivatives needed at all. Okay, this next connection is absolutely crucial, especially when you start getting into differential equations. It turns out that the coefficients of the series, the c terms, are directly linked to the function's starting values. And this slide just shows that connection perfectly. I mean, think about it. If you plug x equals 0 into the series, what happens? Every single term with an x in it just goes to 0. The only thing left standing is that first coefficient, c naught. So the function's starting value, y of 0, is c naught. And if you take the derivative of the whole thing and plug in 0 again, you find that the starting slope, y prime of 0, is just c1. It's a direct link. The initial conditions literally are the first coefficients of your series. Right, so we can build these series. We know they connect to a function's initial values, but what's the big picture here? What's the point? Why do we spend so much time on this stuff? Well, the answer comes down to this really key idea called analyticity. Here's what it means in plain English. For some functions, the Taylor series isn't just a good approximation, it is a perfect copy. It's like the function's DNA. It contains all of its information, just in a different format. And luckily for us, most of the functions we actually care about in calculus, sine, cosine, e to the x, they're all analytic. And this is the ultimate payoff. When we're trying to solve a differential equation, if the functions in it are analytic, we can just assume the solution can be written as a series. This lets us turn a hard calculus problem into a much easier algebra problem of just finding the coefficients. It is an incredibly powerful way to find solutions. So, to wrap it all up, the main thing to remember is this. Taylor series are our way of translating complicated functions into the simple language of polynomials. The fastest way to do that is by mastering that toolkit of common series. And the ultimate reason we do all this is because it's a fundamental technique for solving differential equations. At the end of the day, this whole topic is about using something simple to understand something complex. And that idea, the idea of approximation, is one of the most fundamental concepts in all of science and engineering. The power to approximate is the power to solve. So the only question left is, what complex problem are you going to solve with it?